Hello again. In this video, I'm going to talk about, I'm going to do two examples where we have a hanging sign, a hanging mass, and it's going to be in static equilibrium. In other words, it's not going to move right and left, it's not going to move up and down. So I have an example where a mass is held by two vertical cables, and I have a mass here that's being held by cables that are at an angle. The first thing you want to do is that you want to draw your free body diagrams. The forces acting on this object are the pull of gravity and tension by each string. Okay? Since the tension is going to be the same, we're not going to put a subscript for T1 and T2. So the equilibrium statements are basically writing F net equals ma in the x direction and F net equals ma in the y direction. So basically this is saying sum of the forces in the x direction equals the mass times the acceleration in the x direction. Which means, well, there are no forces in the x direction, which means 0 equals, well, there is no acceleration in the x direction. So 0 equals 0, that doesn't get you anywhere. So now I'm going to do the sum of the forces in the y direction equals m times the a in the y direction. But there is no acceleration in the y direction, so that's 0. So I'm going to think of up as positive. It's just a matter of choice. You can choose whatever you want. So I have t plus t minus the forces pointing in the negative direction equal 0. So I get 2t equals mg. And you can solve whatever you want to solve for. Don't memorize this stuff because it's going to change from one case to another. Another simple way of writing this is just saying, you know what? Since this object is not moving up or down, it just means that the forces holding it up must equal the forces pulling it down. And you can do it quickly. Now let's look at something a little more complicated, and where we have cables that are acting at an angle. So I labeled each one of these as 1, 2, and 3. And I'm going to call the tension here tension 1, tension in number 2 tension 2, and this is not drawn to scale obviously, and this is tension 3. Now, the closer to the vertical the string is, the more of the weight it's going to support. Okay? In other words, the tension will be the greatest for an angle that's very close to the normal. So now this angle is 40, this is 20. In this triangle here, the angle that this string number 1 makes with the vertical is 30 degrees. So the one with the 20 is very close, is the closest to the vertical, which means that's going to have to support most of the weight. And then comes the one that's at the 30-degree angle, and then comes the 40-degree angle. That's with respect to the vertical line, not the horizontal. All right. Now, in order to do these statements, I have to break these forces into their components. Right? So I'm going to try to break them here. Now, I'm going to start with the x component first and do the y component. And you really can do it any way you want. It doesn't have to be that way. So this is the y component. This is the x component. And I do the same thing for T3. And I'll take T2 and I put it outside. So this is T3x. And the one that's going up is T3y. And these are still vectors, right? And if you recall, we did this when we did the vectors earlier in the year. T2, I'm just going to take it and put it out here somewhere, because there's no room in there. So here's T2, and I break that into x and y. And again, it could be y and x. It's just a matter of choice. All right. So now I'm going to see if I can figure out the T3x and the T3y. Well, if I'm looking inside this triangle, right? If that's a 40, this is a 50. Right? Or for T3, I could have done, actually, let me finish it this way and I'll talk about it the other way. This is 50. So the T3x is going to be T3 times the cosine of 50. But let me write the statements first. So sum of the forces in the x direction are 0. The sum of the forces in the y directions is 0. What does this mean? Well, in the x direction, it just means forces to the right must equal forces to the left. Now, to the right, and when I say right, I mean strictly to the right, like horizontal, not like right at an angle. So I see the T1x, and then I have to add the T2x to it. And to the left, I only see T3x. Now for the y, it means that the up forces and the all pointing up must equal the down forces. When I say forces here, I mean the components of the forces, because the components are not actual forces. And that should be equal to m times g. Now, you will have these equations, and you can solve for whatever you need. It all depends on what's being asked and what you have. You can even be given the forces, the tensions, and asked to find an angle, which should not be difficult for an AP student. Now, T3x, if I work inside this triangle here, that should be just T3 cosine of 50. If I do T3y, the y component is the one across from the 50, so that has to do with sine. So that's T3 sine of 50. And you can do the same thing on the other side for T1x and T1y. Now, if you decided not to work with that triangle, let's just say you decided to put to do the y component first, right? So this is T3. So you decided, you know what, I'm not going to do x first. I'm going to y and then x. The bottom line is that you have to reach this point here. So these are the components, this is the resultant. So this is T3x, and this is T3y. Now, the fact that you choose a different triangle does not change the direction of the components. Now, this is 40 degrees. Now, I can say that T3x is T3 sine of 40. But before, it was cosine of 50. And you guys all know from your trig classes that for complementary angles, they swap the sine and the cosine. In other words, sine of 40 is the same as the cosine of 50. That's a trig property that you probably did in your math class. And then once you write your equations and you know how to do the trig here, how to break your forces, you can solve for pretty much anything you are asked to solve for. And that should do it for this video. Have a nice day.